to introduce people, Doug, so
Okay.
it's up to you.
Okay. Well, I'll go ahead and start then. It's a pleasure to have everybody here, and this is really exciting for me. One of the last times I was in this room, I was sitting in the back, and Andrew Wiles was giving the last of his third lectures and announced that he had the proof of Fermat's last theorem. So this is a pretty cool place to be. So what I'd like to do is talk to you today about regional climate modeling. Really, if you get nothing out of this talk except my main point, that would be great. And my main point is that regional climate models produce data, and they produce high-dimensional data. How I analyze it, you can sort of take and leave what I have to say. If you're a frequentist, you might want to leave the Bayesian parts of this. If you're a Bayesian, you might want to leave the frequentist parts. Anyway, but I'll also talk about some analysis methods. This is work that I'm sort of reporting nominally as head of a group. I'm going to be reporting on projects of Carey Kaufman, and that'll be about this functional data analysis of variance kind of models. I'm going to be reporting stuff about Steve Sain. Steve has some new lattice models for spatial data. The other way, just to sort of reference, the other way to sort of reference what I'm going to talk about is when you're comparing regional climate models, you simply have a lot of means over a spatial field. Each of these means is computed from a few observations, and really you want to do some kind of testing or inference on all of these means. And certainly doing all of those individually is not a good idea. The atmospheric scientists have no problems doing that, but it's just not something we would do. And really what the spatial models are about is trying to sew together these means in some kind of coherent way so we can borrow strength across them. So it's that usual kind of statistics story where we're trying to combine parameter in a reasonable way. Okay, what is regional climate about? There are overall results for global warming, for the rise in temperature as we consider a global average to be more useful for people and to sort of inform policy and to sort of get people thinking about how they want to react to this. It's really better to try to understand what's going to happen on a regional scale. Regional climate is more difficult. The overall global effects of increased greenhouse gases on climate are pretty easy to predict simply by energy balance calculations. Basically, there's sort of more warming in the atmosphere, and sort of modulo the feedback, something has to happen. On a regional scale, it's much more difficult to say what's going to happen, and really we have to resort to models. So there's really two statistical problems that arise from this. I'm going to show you some animations of these regional climate models, but basically they're going to produce large spatial fields. And what we'd like to do is simply be able to analyze these in a statistically objective way. And as I said, the second problem is really about we have lots of sample means. They're organized spatially, and we'd simply like to use the spatial structure to borrow strength for them. Okay, and I think that, let's see here. Let me see what the next. Let me give you an idea of what these things look like. I have two animations here I wanted to show you. So let's see. We don't need that. Let me think here. Let's do this one. Okay. And okay, so this is, just see what I got here. That's pretty good. And I'll just put this in, just loop this. Okay. So, clearly I want to make 3 points with this animation. So let me talk about the first one. The first one, this is actually observed data. It's not really observed data. It's something I would call a data product. It involved observed data and running it through a global model to sort of fill it out on a regular grid. But what you're seeing there is over the course of January 29th, those are the that's the surface precipitation field for the globe. And you can see that the swirling patterns are characteristic of fluid motion on a rotating sphere. And you know that looks a lot like the weather patterns that you would see on a TV channel, and it should, because this actual data product is created by the weather models that the U.S. Center for Weather Prediction uses. Now I've put that gray little swatch is kept blank, and that's suggestive of what we'd like to do is downscale those large scale motions to some kind of regional fine scale. And so what we have in the second box is we see the large scale motions as they go across that gray box. This particular domain is a domain for a fairly extensive set of regional climate model experiments that I'll be talking about in a moment. So there's a good reason that that domain was picked. What we have going on in the last box now is we've taken the boundary conditions for this large scale model, and we've simply used these to initialize a very high resolution model that we're now running in the box. And as you can see this run and compare 2 and 3, we see that we get a lot more detail. The question is this detail something related to planet Earth? Is it something that's just related to the computer model that was dreamed up here? And that's a difficult question. Although I should say that the model that's used to generate that third panel is a regional climate model, which is derived from a weather model, and that weather model is very similar to the same that people use simply to forecast weather, and involves all the physics that you might expect built in. What's interesting here is that there's quite a bit of there's surprising, at least to me, coherence in terms of how this works. And let me just stop this at the very end. And I think at the very end here, yeah, at the very end, notice that in terms of the large scale motion, and keep in mind the regional model doesn't actually see anything in the interior of the box. All it's given is sort of the fluxes in and out of this domain. We see sort of this little crescent here of precipitation, fairly blurry, not particularly intense, but we see that structure there, and it's echoed over in the regional model. So what's interesting is that the regional model has been able to take all the information about the fluxes at the boundary and also the winds as in addition to the moisture. It's been able to assemble those and propagate those over time, and produce structures that are similar. The differences in the structures are actually attractive, because the reason we'd want to run a regional model, remember, is to have higher resolution. Part of that higher resolution is to get more of variability and more extremes, and it seems to be doing that as well. So this would be sort of the animations of just to sort of show you this difference between global models and regional ones. the other thing I wanted to show you, and remember the theme of this first part of the talk is simply to convince you that I have high dimensional data. And so what I've done now is I'm showing you two of the models in this in this regional climate experiment. There's actually 6 in this particular domain that I'll tell you about. And so what's different about these models? Well, these models have been built by 2 different groups, and but they're using the same external boundary conditions. You can see that there's some differences between what they do, some similarities. Some of the larger scale structures they seem to capture. Some of the stuff they miss. So I guess a footnote here is that this particular data, there's sort of a very difficult problem here in sort of trying to, in an objective and sort of deliberate way, trying to compare what these 2 things are doing. So as I run this loop now, let me emphasize what climate is and what weather is. So climate is an expectation. It's what we expect to see on the average at a particular location. Weather are the realizations, the sort of instances of that. So the easy way to remember this is climate is what you expect, weather is what you get.
The averaging is over time.
Right, right. In some sense, climate change is an oxymoron, because if you say, well, okay, so I understand climate is an average over time, I understand sort of, you're some kind of in some ergodic state where averages over time or expectations over the measure. Now you're telling me that climate is changing. I don't quite know what that means. And so really the more practical definition of climate is that climate is a little long-term, is a little longer average. It's an average over longer time scales than weather. Typically, taking a 20 or a 30-year average is sort of how climate is defined. And so with that definition, then you would say, well, climate change is actually seeing a change in that 30-year average over time. So you can imagine a 30-year window and just having that advance, and you notice that in that 30-year window, sort of different things are happening as you move that along. But to go back to our regional models here, notice that I'm simulating about a month of this. We could actually think about doing this simulation for, say, 20 years or 30 years. This is producing weather, just like we would observe weather. We take those observations of weather and we average them over a 30-year period, over a 20-year period, just the way we would do with actual data. And so now I think you can get an appreciation that this regional climate problem, especially based on numerical models, is a little bit more subtle, because we have this fairly complex behavior, and we're actually filtering it by producing these long-term averages. And if we see sort of a difference in climate, say for the Pacific Northwest, between this model and this one, it's really going to involve sort of how the flow and how the topography and how other conditions are handled by each of these models. And as you can imagine, that's going to be subtle, and it's going to be effect that's going to be just sort of accumulated over time due to slightly different dynamics in these models. So it's a fairly tricky thing to do. Okay, so that's my...
Just ask a point of clarification. Actually.
Sure.
You're putting in the boundary condition.
Right.
But also some kind of coarser scale information. So you do have some information about what's happening at a coarse scale within the region.
Right.
So why are you not using that as well?
It's not being used because these particular partial differential equations are completely determined by their boundary conditions. So from sort of a fundamental point of view, you wouldn't need it. The other reason you don't need it is that the regional climate models know all the physics in the interior, and there's no reason to use a coarser representation of that. That it's sort of not quite appropriate in a sense.
But you can have you can have an estimate of whether or not your predictions are correct, at least at the coarse scale level, right? Because you can average you take your little coarse
Right.
region within your box.
Okay.
You
Okay.
take your predictions there and see whether or not it matches the average prediction over.
Right. So in this particular case, the term that people use is the exterior forcing. The forcing here, we're actually forcing this by a version of observed data. So it would make perfect sense to average this up into the coarser grid cells and compare it to this data product. But the other experiments people like to do is simply run a global climate model and then use the results from the global climate model to force the regional domain. In that case, it doesn't really make sense to compare the regional model to the global one because we know that the regional one has better physics and should have more veracity than the global.
Doug,
Yeah, Peter.
What about the fact that, I mean, presumably you have actual observations in this region, so you can presumably use those for validation.
Yes, you can. The gentleman in the back sort of alluded to this scale problem, and the scale problem with observations even get worse because an observation, a weather station, is simply a point value. These regional simulations are on the order of about 50-kilometer grids. The actual data product I was showing you, I think, was more like on the order of hundreds of kilometers. So there's this mismatch between different scales, and it's hard to sort of decide how much discrepancy you would see that's simply due to this aggregation process. So there's a lot going on here. Having said all that, having sort of wrung my hands and said this is a difficult problem, the regional climate modelers really don't use a lot of sophisticated statistics. And I think that there's a lot we can do to help them. If only to tell them, please don't take means of all of these and divide by the standard deviations and contour things at plus or minus 2. I mean, it's sort of like they do very simple things. Okay, so you have an idea of what this stuff is like. Very quickly, let me go through this in words. A GCM stands for a general circulation model. You can also call it a global climate model if you want. It's a coupled system that involves a lot of other components besides the atmosphere. It involves the ocean, the ice, land processes. There's also current development is in feedbacks between human activities like releasing other kinds of gases besides CO2. The sort of rule of thumb is typically a sort of full state-of-the-art global climate model. You can simulate about 5 years of the Earth in about a computer time day, a wall clock day. And the reason this is the reason that's we have that relationship is basically the modelers want to be able to develop the model in sort of time spans of about a week. So you figure you run the model for about a week, you get about 20 years worth of data, 30 years worth of data. You can average this up to see what kind of climate your model is producing, and you can decide what to do for the next week over the weekend. This is a typical sort of working resolution for the NCAR climate model. Here's a picture of our new computer. If you haven't seen supercomputers, they're sort of interesting objects now. Basically, the supercomputers of the future will be, you will take I don't know what the British equivalent of this is, but you would take a Costco, you would take a big sort of warehouse supermarket, and raise the floor, put in air conditioning, and you would just sort of fill this with boxes the size of refrigerators, and you would fill this with a world-class machine may have hundreds of these sort of refrigerator-sized boxes. This
It used to be like, right?
Pardon?
That's what it used to be like.
Yeah. Although I think the scale is actually getting much bigger now. The projections are that these sort of, in a few years, these large computing centers are going to draw 5 to 10 megawatts of power, and so there's actually this funny back and forth as to say, well,
like contributing to climate change.
yeah, exactly. Are the calculations of climate change actually contributing to part of the problem, which is sort of anyway. So this is our new one. This is sort of a row of these sort of refrigerator size boxes. It's called Blue Fire because it's an IBM machine, and we sort of, for some reason, we name everything IBM. It always has a blue prefix. But the important thing is that even though this is sort of state-of-the-art computing, we're sort of throwing sort of the biggest hardware we have at it, there is this resolution problem for the global models. And I've already walked you through this as to why you want to do regional models, but here's a very graphic illustration. So thunderstorms are very important in terms of essentially moving heat from the surface up into the atmosphere. If you think about it, what we take for granted is actually a fairly strange state of events. It's warm at the surface, it's cold up above. You'd say, well, that's the way we want it, to be able to walk around on the surface. However, you know that warm air rises. So at some point there has to be an overturning. That happens dramatically with thunderstorms, especially over the equatorial Pacific. These thunderstorms are one of the big mechanisms of moving heat from the surface up. But thunderstorms are not represented explicitly in models. They're not even, unfortunately, they're not even represented explicitly in regional models. Here's another example of the difficulties of these large global models. This is a picture in Colorado, looking from the plains onto the foothills and then to the higher mountains at the Continental Divide. Everything you see here, all these different variations in the land, would be in one global model grid box. And so when I say this is all in one grid box, it means that everything you see here is getting a single surface temperature, a single wind at the surface, a single amount of moisture. It's all reduced to a zero-dimensional point, or just a one-dimensional column. So again, sort of this idea of using global models to try to understand local effects is not possible. And so this is another argument for using these regional climate models. Even a resolution of 50 kilometers by 50 kilometers, which is sort of the working regional climate resolution, is probably not great, but it's a lot better than the sort of hundreds of kilometers scale that the global models can achieve. Again, here's an example based on simply topography. If you actually look at the global model representation of topography on the western U.S., the Rocky Mountains end up being just sort of this gradual set of hills that gradually increase and then tail off into the Midwest. There's not sort of these sharp rises that you can represent with high resolution. Okay, so the animations that I showed you are with the North American Regional Climate Change Program, NARCAP. This is a large effort. And what I want to emphasize here is the statistical design aspects here. There are 4 global models in addition to that data product that I was showing you. So there's actually 5 different things you can use for global inputs into this domain. And in terms of what we're running on the inside, we have 6 different regional climate models to run. So we actually have 25 separate cases. Let's see here. We actually have 30 separate cases because we have 4 GCMs and using observational data, and then we have 6 regional climate models that are running. And in the second part of this talk, I'm just going to mention a strategy for sort of handling this kind of factorial experiment. Okay. Well, I think that the animations make it pretty clear that there's data. The other thing that you need to know is, and I think this is obvious from the animations, I say, well, just run these regional climate models 30 years, find the average at a particular point. That'll be an estimate of the climate. Clearly, these are nonlinear and they're chaotic systems. If I make slight changes in those external fluxes coming in, I'll actually get a different sequence of weather that I see in the interior. The different sequence of weather is going to give me a slightly different 30-year average from one that I found before. So there's actually uncertainty in this. This is basically the uncertainty we see day to day in the weather. In June, we have essentially the same climate, although we see different days are varying. And that's referred to as natural variability. So in the models generate natural variability. Of course, we have natural variability in the weather and climate outside. And so really, this is an argument that we really have to use statistics for this. Another way to say it is that we have all of these means that are an estimate of climate at these separate locations. And of course, all those means have some error in them. Okay, and I'm going to now switch gears. I'm going to talk about a slightly different regional experiment that Steve Sain has worked through. The punchline here, and I'll go through this fairly quickly, is using lattice models to model the spatial structure in these fields. And here's the domain. This data is from Ruby Lung, who is at Pacific Northwest Labs. Typical of these experiments, we have these are going to be run during a control period and then a future period from 2040 to 2060. In the future, so I should say that these particular experiments now, the global model is not data anymore because it'd be very difficult to get data for 2040. This is an NCAR global model. In order to run this model in the future, we have to come up with some kind of prescription of what is happening in the future, especially in terms of greenhouse gases. And so the particular climate scenario that's being used here is a 1% yearly increase, which is sort of in the mid-range of what people forecast in terms of human activity. Okay, so I'm going to show a response where we're going to look at summer and winter temperatures and precipitation across this domain. And we really want to ask a very simple question. How will things change as compared to control versus the current climate versus a possible simulated future? So here are the differences. And just moving across the top here, what we have is temperature on the top, precipitation on the bottom. What I actually have here is three realizations of this. So what we're actually looking at is differences between current climate and future climate. That's what each of the fields are. Temperature on the top, precipitation on the bottom. Now, what are these columns? Well, these columns are representing natural variability. That is, for this particular experiment, the global model was perturbed just a little bit. And so that, as I said, that creates a little bit different regional patterns within it. And what you're seeing here is simply just the sampling variability, if you will. If this was a longitudinal study, we'd be looking at 3 different subjects, and this would be the variation in the subject response. So clearly we're seeing differences here, and this is sort of where we have to do the statistics. So part of the idea is that we know that the model is simulating some kind of difference in the climate. And what we want to do is tease out that mean signal from the variability that we see here, or at least try to characterize what that variability is around the mean field. Yeah?
How confident are we that the models are actually reproducing the natural variability, the real variability?
we don't, the confidence in that is difficult to assess, because the models are built with a view to the understanding of current climate. When you compare them to current climate, they do okay. Where they don't work well, the modelers say, well, we haven't quite got the physics right, but overall we have the basic physical processes. So it's a very weaselly kind of conversation to have. Yeah. So we don't know. And I should say, in all of this talk, I am simply talking about analyzing these model results. Clearly, we can shift things slightly and talk about trying to validate these models against data, but I'm not going to really address that here. It's enough of a problem simply to take their model output and try to come up with some objective analysis of it. Here's the kind of inference that we found that's useful. I made up sort of an interesting probability event in terms of the climate fields. So the difference in winter temperatures between current climate and future climate is warmer. So that's a warmer winter. This would be a drier winter, that the difference in precipitation is less than 0. And this is all done in a Bayesian context. So what I'm actually plotting here is posterior probabilities of that event happening with the climate fields. And so you can see that there's warming and drying in the Northern California, sort of high probability up in here. There's also high probability of this happening over here. For skiers, this is of particular concern because there's a very, one of the nicest places to ski in North America is right about here. And so having warmer winters and drier winters is not something good. On a less frivolous side, of course, this kind of event is a simple caricature of having reduced snowfall in the Sierras, having perhaps earlier melts, and that has quite an effect on sort of water supply. So that's the kind of thing that we would do. So what we're trying to do is take sort of these global prescriptions, 1% increase in CO2, and trying to relate that to a little bit more specific events for regional scales and attach probabilities to it. So that's basically the idea. So what I want to do is, I've already, having given you the results, I want to explain how we do the statistics of this. Very briefly, it's a hierarchical model where we have a data level, a process level, and then we have some priors. Typically the priors are diffuse, so we're really not putting in a lot of information at that level. The priors are really just sort of a way of making these terms in the regularization sort of stable, is one way I think of it. At the data level, we have a very simple model. Remember that the climate, we have these sample means that are just difference between current and future climate. We have all of these means that are sort of based on about 20 years of data in both of those periods. We say each of those means has an expected value, theta ij, and it has some variance, and that variance is due to the natural variability in these models. The ij indexes locations over all these grid points. There's about 2,000 grid points in this. It also indexes over the kind of variable, temperature or precipitation. And if you remember, I had 3 columns. Those 3 columns are technically called members of an ensemble, but you can think of them as replicates in a design. So we have, I don't know, depending what you want to call this, we sort of have a one-way analysis of variance or a two-way analysis of variance. But anyway, we have means, we have replicates. This is all looking pretty familiar, except we have a zillion of these things. We have more than 2,000. So the way we model these is using a lattice model. And the easiest way to think about lattice models is that on a regular grid, we write down the distribution of a point in the grid based on its neighbors. And typically you do this thinking about multivariate normal fields. So you write down the conditional expectation of a particular lattice point given its neighbors, the variance given its neighbors. And this is sort of the skeleton of the kind of relationship Steve used. Of course, the mui's and the b's and the tau's are things we have to estimate. Now, what's new in this for Steve, and I don't know how well you can see this, is how to handle sort of a multivariate response. The way to do this is that we have nearest neighbor relationships between temperature and the temperatures neighboring it. We have the same for precipitation. But to build in the multivariate relationship, we have a direct relationship between temperature and precip at a location. And then finally, there are these neighboring relationships that are crosses. That is, we're also allowing for precipitation neighbors to affect the temperature in the center of the lattice, and also temperature neighbors to affect the precipitation. These introduce a few more parameters, but they're all easily handled sort of in this lattice framework. Okay, so I put this up. I'm not going to take too much time explaining this, but I put this up simply to say even the output of the statistical analysis is a little bit difficult to summarize. So what I've done here is imagine that we've done the Bayesian hierarchical model. We've gotten these posterior means for the different theta ij's, the climate response for both temperature and precipitation, and we simply just want to summarize them. How do we make sense of them? Well, that event, which was being, let's see, it would be being below zero for precipitation, above zero for temperature with high probability. That would be these red points here. What Steve was trying to do was just to cut up this scatter plot in a way that sort of made sense in terms of clusters. This is I think a mixture of multivariate normal clusters where he allows for some overlap between them. But he just fit some clusters and then registered them with colors on the map, and so you can see sort of how this scatter plot of the climate change sort of is related geographically. We're open to other ideas how to deal with this. It's sort of complicated. The other collaborator in this is this gentleman. Does anyone recognize who this is? Yep, very good. I tried to find a picture of the web of Noel smiling. I only found one picture, so luckily he's not frowning in this. The reason I put Noel up here is that Noel, as you know, has worked quite a bit with spatial models. What I'm plotting here is the scatter plot of the parameters that describe the connection strengths between precipitation neighbors and a center temperature, temperature neighbors and a center precipitation value. And what we're seeing here, because the inference shows that it's not on the diagonal, it means that there's an asymmetry here. And I think that the way the asymmetry goes is that precipitation depends strongly on its neighboring temperatures, then temperature depends on its neighboring precipitation values. And Noel says that he hasn't seen this very often in lattice models, or perhaps this is the clearest case of it. So it's sort of an interesting sort of multivariate new aspect that's been turned up here. I should say that these lattice models are all stationary models, and there's a lot of potential to sort of embellish these and make these a little bit more elaborate, adapt to topography, adapt to other features. Okay, so that's the first part. Now what I want to do is talk a little bit about functional ANOVA. Let me just pause here and ask if there's any questions at all.
In this dependence of temperature and pressure neighbors and vice versa, would
Yeah.
there be sort of a directional issue?
Yeah.
And is that part of the modeling?
Is it an issue? Yes. Is it part of the modeling? No. No. It's
Otherwise, wouldn't you in some sense be averaging a linear effect, and if you were seeing something, it would be the sort of the quadratic part or something?
Well, let's see. So one-dimensional effect, if the temperature, say, to the east of me, so I'm jet lagged. I have no idea what direction this is, but the temperature to the east of me matters more than the temperature to the west of me. So that would be one sort of more complexity. Now, whether or not saying the temperature to the east of me, I'm not only related to a linear function of that, but perhaps a quadratic function.
So there are 4 different coefficients.
That's right. That's right. That's right. Okay. Let's see, Mike. How long do these talks go? Is it 45 minutes and a postscript, or an hour and?
Up to an hour.
Okay. I think what I want to do is go through the functional ANOVA fairly quickly, and then just leave it open for questions, because I don't want to go too long here, because it's sort of an easy idea. So I talked about NARCAP. I talked about Ruby Lung's regional climate models. Here's yet another numerical experiment. So, part of what you should get out of this is that there's a lot of these regional climate sort of work going on. It's a little bit different than the global models, where there's only really about half a dozen big global models that people can do science with. The regional models, they're much more diverse. This is suggestive of the kind of NARCAP experimental design. Across the columns, we have 2 different global models. The column on this right-hand side is actually the Hadley climate model from the Hadley Center. The rows are 2 different regional climate models, and this is a complete 2x2 factorial. Unfortunately, this is the only complete 2x2 factorial in this large European effort, and so there's something funny about just getting reasonable design of experiments into this stuff, even though they're using lots of computer time, committing a lot of resources to do this. But anyway, we have a nice 2x2 experiment. What is the response? What we're looking at is the 30 years of summer temperatures in the future from based on a particular scenario, and I can't remember exactly what this scenario involves in terms of greenhouse gas release, but it involves some kind of increase. Okay, well, what we'd like to do is take these fields. Clearly, they have variability between them. We'd simply like, for the regional climate modelers, be able to summarize what the effects are. And the way to see this, what I've done is just taken that table and expanded them a little bit. So remember that these are the global models, the columns. These regional models are forced by the same global model here. The regional models are forced by the Hadley model in this column. And of course, this row is one regional model. This row is one regional model. The first thing that we can do is we can average them all together and report a grand mean. So this is the average climate response for all the models. We can also calculate row and column effects. Notice that the effect of the global models has a lot smoother structure. That's the difference between forcing the regional models with one global model versus another. Along the other side here, this is the effect of using one regional model versus another, swapping those in and out, keeping the global model the same. And then finally, to round this out, we have the interaction. And so I'm sure all of you know that really taking these 4 and is simply and then going to these 4 is simply a one-to-one transformation of these means in sort of a different way. The statistical problem is simple. We'd simply like to characterize when when is something big actually exciting or significant, or has a high probability of not being zero. Remember that all these models are realistic enough where they simulate natural variability, so all these means are measured with error over this short 30-year period. Okay, so again, Carey is using a hierarchical model here. So we have the response at a particular time is going to be the mean, and I think the I represents regional model, the J represents global model, T is time, we have 30 years here. This is our internal variability, this is our climate mean, and then X is a particular grid box location. So this is really very similar to doing a one-way analysis of variance or a two-way analysis of variance with interactions, except we have all of these means. The actual responses here over the locations are sewn together using in Bayesian language here, we're putting a Gaussian process prior on these surfaces. But really from a frequentist point of view, when you sort of dig through all this, it's really just doing a regularization of the fields. And the regularization is quadratic because we're assuming Gaussians. We're using a Matern family, which looks a lot like derivatives. So in some sense, you could say this is really pretty similar to doing something like thin plate splines in terms of estimating the surfaces. So let me explain the results here. So this is my last overhead. I always like it when the speakers say, "This is my last overhead," because then I say, "Okay, now I can just concentrate on this, and then I'm done." So here we are. However you want to describe how I got these surfaces, whether they're posterior means or if they're the result of solving a variational problem with a regularization. From the Bayesian point of view, I can also get sort of posterior uncertainty information from these, and that's what I'm summarizing here. What I'm doing is I'm looking at something like an F statistic, and I'm simply showing you places where the F statistic is large. And so if I compare the regional climate model results to natural variability, and remember I have that because I have the data at every year over 30 years, I can say, well, how is the variability in this response due to the regional model? Is that more variable than natural variability? And we say basically, no, not really. There's only a high probability of seeing the regional model climate differences sort of large, sort of along these coastal values, or sort of in complicated the sea in between Ireland and Scotland. If we look at the effect of the global models, the variability in the global models relative to natural variability, so again, this is just looking at a probability of a, sort of like looking at this F statistic, we see that the probabilities are large on the boundaries here. And so this could really be due to simply just differences in the global model having different boundary conditions around the edges. And then finally, if we compare the regional model to the global model and ask which has more variability, we see that there's high probability that it favors the regional model in places where things are complex, along the coastlines here, along the top of Scotland, where there's topography. So let me just wind up things. So regional climate model output provides many challenges in analysis that is similar to observations. So the one thing I should have said here in the initial part is that the global models, the regional models, are deterministic models. There is no stochastic elements in them. Their seemingly random behavior is due to the strong non-linearities that are modeled, but they're you run them another time and you can get the same results if you're careful to start them exactly in the same way. Clearly they're interesting data though. I haven't even talked about validating the models, or sort of following up on Serge's initial remark. But I've covered some ideas for spatial fields. So Steve is working on lattice models. Another alternative to handle these large spatial fields is to taper the covariance, to deliberately introduce sparseness in them, hard zeros that make the computing easier. And then Carrie is talking about ANOVA decompositions as a way to sort of summarize these things. Okay, thanks a lot for your attention. So,
Good question. I noticed that you had a trend in the ANOVA decomposition. You had a
that's
trend.
right.
Was it significant?
Yeah, because over that period there is a warming overall. And
So what does it mean, this trend? That there's a trend difference between the models and
I think, I'm not sure. I want to say it was a single trend, and it was just removed from all of the fields, and it's sort of like putting a trend in the grand mean. And I would guess that Carrie didn't do any more detailed modeling of the trend because it really wasn't present once she took out the overall pattern. So there is this very clear and consistent signal of warming due to in-house greenhouse gases that you would see through here. So it would make sense to have just a single trend. Yeah, Peter?
Can you just give a qualitative idea of what kind of variability there is in the projections of the different models? I mean, say, over a reasonable area like this. I remember long ago that was when primitive days when there were two models, one of which claimed that the southwest United States would be 5 degrees warmer and the other one claimed it would be 5 degrees colder.
I think in terms of precipitation, you can, even in the latest round, you can find regions where some models will say there's a drying and others will say that it's getting wet. The generation of models just before this one, the NCAR model actually produced dry enough conditions in the southeast that would turn all the pine forests in the southeast to more of a savanna. And but the model actually, the land part of the model actually prescribes pine forests. So you have this weird thing where there are forests growing there even though they're not getting enough water to actually grow there. So there's sort of weird things like that in the model at regional scales. So I would say that it's still very difficult to say much at scales larger than sort of a smaller than a continental scale. It's felt that if you think about the western U.S., the northern part will get wetter, the southern part will get drier. Colorado is sort of a swing state in many ways, but it's not clear if Colorado is going to participate in sort of the wetter regime or the drier regime. It's the other qualitative thing that there's a consensus about is that the way wetter events will happen is that they may be more extreme events. So you may see more precipitation, but it'll happen as just sort of falling at a faster rate. You'll just have basically bigger storms. So in the winter that may mean larger snowstorms in Colorado, but they may melt, but the snowpack may melt sooner due to the warmer temperatures. So what I'm talking about here, I mean, you asked a quantitative question, and I've subtly switched into qualitative things.
That's a qualitative question.
And really that's sort of the current state now of the knowledge. And the whole debate about climate change and sort of the whether it's happening is part of the hedging of scientists to be sort of unwilling to go by these numbers exactly, but to give this qualitative thing, because really at the end of the day, I think there's a feeling that the models are still qualitatively reproducing the processes people expect, but the quantitation is difficult. Which is part of the reason we want to get into the statistics of this, to help people understand how to do this correctly. So, yeah. So, yeah, Yasmin and Ed, do you have anything to add here? Because you've sort of been around this stuff too. And
well, probably not a whole lot of intelligent things to say, but when you're talking about boundary conditions, you're really talking about boundary conditions on a fairly large scale to calibrate these regional models.
Mm-hmm. Mm-hmm.
And the boundary conditions sort of are very locally dependent, really, aren't they, for the regional models?
Yeah. Yeah.
So,
yeah. Yeah.
When I was in Carl last time, we talked about the idea of chaotic behavior of these models. Now, you're saying that if you reproduce them, you're saying you can reproduce them, but if the boundary conditions change a little bit,
right, right,
that means the predictions change a lot, potentially.
That's right. Although what will change a lot is the weather that you're getting through the region. But as you average that over time and sort of accumulate a climate expected value, you would expect that not to change much if the boundaries are varying in a climate kind of way. So it's.
But I suppose the big issue is, what's the scale of time when you average over time?
Mm-hmm. Right. So the regional modelers do play around a little bit with the domain, and they're careful to actually analyze results on a domain that's smaller than the larger domain that they're actually using for the forcing. So there's time for the model to sort of adjust. But all of this is very much sort of craft and subjective, and sort of you ask, well, what's the best thing to do? And the best thing to do is what the best group is doing. It's not clear that it's objectively can be justified. It's just sort of what the
Comment to what extent this is remote sensing dependent versus local. So temperatures are taken essentially at points.
Mm-hmm.
But you somehow calibrate these, at least the global climate models, you calibrate over very large regions, and so presumably that's remote sensing measurements. Is that right? So the data product that I showed you is technically called the NCEP reanalysis, which is simply taking the stream of all the observations that come into weather forecasting and simply running the same weather model to take these irregular and scattered observations and produce consistent meteorological fields every 6 hours. So that process is what the Met Service does every 6 hours to produce a picture of the atmosphere. If you just run the same model consistently over 50 or 30 years, you produce these data products. So in the NCEP reanalysis, I think that they use satellite data when they have it. So once you have these observations on a grid, I think I would guess probably the grid is finer than the one I'm actually showing, but they simply average those together and produce a gridded average. So another way to say this is that this is the atmospheric sciences community's way of doing spatial statistics. They have irregular data. They want to produce a regular field from it. Their approach is not to write down covariances. not to write down a statistical model. They simply say, let's take a physical model and initialize it around these observations and sort of run it forward in time and let it equilibrate, and it sort of generates these processes, which are then their spatial.
Essentially, sort of imputation process, right? Model-based imputation process.
Yeah, yeah, sort of. Yeah, it's just another approach. I mean, it's a physically based one, as opposed to a statistically based one. Yeah.
But if you impute this stuff, if you impute by a physically based model, is long-term averaging going to be the physical based model?
Well, I mean, it's the analogy would be if you do spatial statistics and keep estimating at a point where you don't have data, is the long-term average of that point, is it simply going to be what you prescribe in your statistical model, or will it be related to data? Well, it'll probably be related to data, because you wouldn't be doing this if you couldn't make some kind of prediction informed on data at that point. So that's what it is. Subtleties like extremes and relationships between variables may actually be built into your physical model. So there may be some layer where that's actually an issue. Yeah, Peter?
Just coming back to the issue that I think was raised at the beginning, also about possible, sort of calibration using data within the region. Now you were saying that it's much too coarse, and you just have single measurements at widely spaced stations. But presumably, again, maybe if you average over time these measurements, I mean, at some scale, you should be able to get some sort of validation.
Yeah. So that's true. If you actually average over longer time scales, that you should be trading sort of time for space in some sense. But it's I'm not sure how you would actually determine what that relationship is. So yeah. The validation problem is really hard. I mean, we don't have a lot of data to compare these models to. The models have been built in sort of cognizance of what that data is looking like. When the models don't match sort of surface data perfectly, that part of the response of the modelers is that, well, we're more interested in getting the processes right. I mean, we want to get flow, we want to get the monsoon flow coming into the southwest U.S. I mean, it's not as important to get the amounts correct, but we sort of want to get that kind of flow structure. So they're like us. They can sort of argue all kinds of sides of what they do and explain why it's a good thing. So, yeah.
To create a few guilty consciences, I've got a postscript if you can be bothered waiting for a few minutes.
Do you want me to put up this screen, Mike?
It doesn't matter.
Okay.
Project it this way.
Anyway, it's comparatively small scale and probably more suitable for computer science. About approximate Bayesian inference. So, beta is a parameter, y represents data, and we've got some latent or missing variables. And of interest is a posterior distribution of beta given the data. And what what would be done, I suppose, in modern Bayesian statistics would be that you would use MCMC to generate realizations from the joint probability function for beta and the z's, y, and then pick out betas to give you an estimate of this. So here's a formula. Generally, that this would be the formula for beta on its own given y. And we've got a lot of factors, one for each observation. This one will be for the prior, and then Ti for the ith observation, T1 for the first observation. Now I'm going to talk in detail about this trivially simple one-parameter problem, mixture of two known densities. And the natural prior is a beta, and the factors going with the observations are the mixture type model. So when you put them all together, you get a rather unwieldy posterior density. If we knew what the identifiers of the mixture components were, then each of these factors would look like the prior in the sense that it would be power of beta times power of 1 minus beta. And if the observation came from the first component, this would be 1 and this would be 0, and vice versa, it came from the component. And the crucial thing to remember is that Zi plus 1 minus Zi equals 1. So what this means is that if you worked out the precision of the posterior density in this circumstance, which would be itself a beta distribution, precision of it goes as n, because it goes as the sum of these things. So that's complete data posterior. If you don't like doing MCMC, then you look for approximate non-simulation versions, and the one that you have a lot in the computer science literature was sort of variation Bayes. And the idea there is to take to obtain an approximation for the joint posterior function for beta and z, and to choose one that gets as close as possible to the correct joint posterior in some sense, in particular in a Kovac-Leiber sense. To make an approximation, you make assumptions, and the assumption that's made is that this approximation factorizes into a beta bit and the z bit. Well, if you do this, you find that the approximating posterior for beta is also a beta distribution. In other words, it's the same type of distribution as the conjugate and for the complete data scenario. So again, it's the prior bit times the product of bits like this, and these bits are all of the same nature as if we knew what the true identifiers were, except that these Z tildes are not 0 or 1, they're typically fractions. On the other hand, Z tilde plus 1 minus Z tilde is still 1. And therefore, this variational approximation to this posterior distribution has a precision that goes as n, the same as if we actually confirmed the identifiers of the observations. And therefore it's too big, because if you were to work out interval estimates on the basis of this approximation, it would be too narrow. It's as if it's the same size as if you actually confirm the data, which you don't. How big should the precision be? The answer is that it should be consistent with the properties of maximum likelihood estimation corresponding to mixture data. Eventually, for large samples, the actual correct posterior from the mixture data should be essentially the same as a normal approximation, in fact, based on maximum likelihood. So the variational method fails on the grounds of being too precise. But there is another approach that's come up in computer science called expectation propagation, developed by Tom Nychka, who's in Microsoft. It does have quite a few antecedents. For instance, in the statistical literature, which Nychka does acknowledge. Anyway, the method here is to say, well, we are going to create, for this particular simple problem, a beta approximation, which can be represented by a product of factors like this, and each of the tilde factors is the power of beta times the power of 1 minus beta. So putting them all together, we do get a beta approximation. These things are calculated iteratively. At a particular stage, you take this function here, you drop out the approximating factor, and you put in the correct factor for that observation, and you turn it into a density, which will be a mixture of two betas, in fact. And then you collapse it down into a single beta. You choose a new beta approximation, which amounts to choosing a new beta-type factor here, in such a way that this is as close as possible to that in some sense. And you can do this either using a Kuhlmann-Leibler criterion, or you can match moments. You can match the first and second moments. And that, given that, you feel you've got a chance for this to work the way you would like it to work. Because asymptotically, all you really need about this posterior distribution is that the mean and the variance turn out to be as you want, or the mean and the precision turn out to be as you want. Because you would use eventually Gaussian approximations, so you just need the first two moments. Anyway, so you do this, you iterate through the observations and keep going, and you get convergence. And it turns out, I don't think this, I haven't seen this anywhere else, but anyway, it turns out that asymptotically, the precision that you get eventually from this beta approximation is correct in terms of matching what you would get from maximum likelihood. And essentially, for each of these factors here, if you take the Zi, the two Z star bits, and you add them together, they're no longer equal to 1, which would create precision that's too big. They're less than 1, and they're just the right amount less than 1 to fit with maximum likelihood. So for this problem, I'm sure I haven't got all the points of rigor correct, but I feel fairly convinced that for this problem, this expectation propagation algorithm creates, if you like, a valid posterior approximation to the posterior. Anyway, most people in the audience probably haven't heard of this method, but it is something that has been applied a lot in computer science. What's obviously of interest is to look to see to what extent this sort of behaviour applies to other examples. And I found a few that it does, and I found quite a few that it doesn't. Started talking to Niels Hjert, and the hope is that, well, it'd be nice to know, is this just a lucky example, or can we what I was going to say. You may or may not want to comment.
I'm just curious. I just ask a question. When you say the precision is that n is too large, you don't mean the order, but simply that the constant is wrong, right?
Yes, that's right.
Now, are there comparisons made of methods like this with sort of crude methods of getting at the maximum likelihood estimate? Or, you know, you have an estimate based on the first 2 moments, and then you take one step. In terms of performance, I mean, you know, so I mean, you have these elaborate algorithms, but you know, you need them. I mean, say in simulations. Are the simulation?
Well, in this particular, I should have brought another picture down. This suggestion occurred to me because I and a colleague did an example where we did an MCMC on this and created a density estimate and did not expectation propagation but a recursive sequential version of it, which is called the probabilistic editor, and drew the picture for the beta, and the two curves were essentially indistinguishable. And simulations by Nychka in his thesis and Matthew Stevens in his thesis with versions of this showed that, at least empirically, for this problem, things behaved well, but it didn't pin anything down from a semi-theoretical point of view.
I guess I'm just sort of asking a more general question in your experience of the computer science literature. I mean, do they actually try to use as approximations the, if you want, more classical things that are suggested by the more classical statistical literature, or do they? So are these used in situations where really you can't check more or less, and they just?
Well, the methods are applied to more complicated examples than this, but on the other hand, they're also they're applied to comparatively. They're applied to situations where MCMC is feasible, as well as possibly to other much larger scale problems where it's not so easy. But I'd say there isn't a very large amount of empirical comparisons, certainly not theoretical comparisons. David at the back, he's the one that's likely to contradict me if anyone is.
Yeah, well, I mean, I think that obviously in computer science, you know, you're looking at something where Nychka and people apply these things. They're huge problems, right? So one of them, they claim, you know, the largest Bayesian problem which is solved on a daily basis in the world is predicting what's happening in games, and online games. It's this true skill algorithm, where it's just not feasible to run something like MCMC, basically. And they're, you know, these EP algorithms, they converge extremely quickly, and they work exceedingly well, better than anything that's ever been seen before. But of course, I mean, if you tried hard enough, you can always make an MCMC method work, right? And if you were smart and you figured out, you know, what proposal to use, maybe you can get that to work as well. But I think the point here is that these methods, there's certainly classes of problems in which they work pretty much out of the box, and they're extremely quickly convergent. And that's a big win. You don't have to spend a lot of time worrying about proposal distributions and stuff like that. So, I mean, just as a comment, this kind of area is closely related to cavity methods in theoretical physics. And the guys in the other program will know a lot about that, where basically the idea there is that you sort of remove a particular point in the field which creates the cavity, and you replace that cavity with the correct points processed from the field, and then you re-estimate. And this is a similar kind of vein.
Then there may be some theory there too.
Yeah. But I think, you know, what's interesting about this, I think, this class of problems is, if you look at information theory, that's probably the biggest, maybe interesting area where you've got a huge, in error correction right? So you want to solve a kind of a decoding problem there, which is typically intractable. So people have tried, variational techniques. They tried Monte Carlo simulations, really complicated Monte Carlo simulations. EP or variants of EP work exceedingly well. So they're closely related to the turbo codes or turbo decoding. And there has not been yet, despite 10, 15 years of trying, anybody has not managed to get an MCMC method which works anywhere close to as good as theirs. So there is something non-trivial behind these methods. I think it's not really understood, and it's difficult to understand maybe what's going on. The information theory guys have made some progress. They can analyze on average case analyses what's going on, and indeed there is really there is something, at least particularly in sparse type systems, some highly non-trivial results here.
I guess, I know I wasn't really asking at all about comparisons to MCMC.
Yeah.
But more to, even in these very complex situations, are there at all ways of at least helping the algorithm, if you want, or somehow, using analytic approximation at some point or other, which might simplify things. Because, that's
Yeah.
suggested by Mike's presentation, which is basically trying to sort of check the algorithm through in a situation you can actually make an analytic.
Yeah, I'm not quite sure what you mean by analytic, but do you mean some kind of like Laplace style approximation?
Yes,
or,
that's essentially what the posterior.
Yeah. But a thing that some people have tried is, if you think about it, these algorithms, these EP style algorithms and others are local algorithms in the sense that the idea is to take a term and replace it, locally with another kind of term. The Laplace style things are what you might consider a global approximation. So the question is there a way to integrate perhaps the two to make another algorithm which sort of gets the best of both the local and the global? And there are methods which attempt to do that, to come up with some kind of, to force the local statistics to be correct with the global statistics as well. And that's been attempted, yeah. I forgot what it's called actually. The Manfred Opper has a technique to do that. So there are yeah, and the cross product of all these things, I guess, is doable, but it's very difficult to analyze actually what's really. So there's only kind of empirical evidence, I think, to suggest that in some cases it might be working
One last thing to mention.